Good evening everyone and welcome to my channel. We'll be continuing with the linear algebra series in eigenvalues and eigenvectors. Today we are going to talk about diagonalization of a matrix and how does the algebraic and geometric multiplicity affect diagonalization. Let us begin with definition of diagonalization of a matrix. The definition goes like this. A square matrix A is said to be diagonalizable if there exists a non-singular matrix C such that D is equal to C inverse AC is a diagonal matrix. In other words, a matrix similar to a diagonal matrix is said to be diagonalizable. Let us see one example for the same. Consider the matrix A given by 5, 4, 1, 2 and let's take C is equal to -1, 4, 1, 1. Since C is a 2 by 2 matrix, we know that its inverse is going to be. Let us now consider the product C inverse times A times C, which is going to be -1 over 5 into the matrix times A, which is 5, 4, 1, 2 times C, which is -1, 4, 1, 1. We'll be first multiplying these two matrices and that gives us -1 over 5 here times 1, -4, -6 and -6 times the matrix -1, 4, 1, 1. Now let's multiply the last two matrices which are remaining. We are going to get -5, 0, 0 and -30. And lastly, moving the -1 over 5 as a scalar inside, our matrix reduces to 1, 0, 0, 6. Now it can be seen that the result which we have got is a diagonal matrix and hence we come to the conclusion that A is diagonalizable. In an earlier video, we had seen how to calculate the algebraic multiplicity and geometric multiplicity of eigenvalues of a matrix. We are going to today state a result that helps us identify whether a given matrix is diagonalizable or no with the help of algebraic and geometric multiplicity. It goes like this. A is diagonalizable if and only if the algebraic multiplicity and geometric multiplicity coincide for each eigenvalue of the given matrix. A is also diagonalizable if and only if A has n, where n is the order of the matrix, linearly independent eigenvectors. And we also have that if A has distinct eigenvalues, n distinct eigenvalues to be precise, where again n is the order of the matrix, then A is diagonalizable. These results helped us to decide whether A is diagonalizable in a quick manner. Now let us get through a problem wherein we are going to check whether the given matrix is diagonalizable, and if it will be diagonalizable, we are going to find the corresponding matrix, the corresponding non-singular matrix C. So consider the matrix given by 1, 2, 3, 2. To begin with, let me call this matrix as A. We are first going to find the characteristic polynomial of A, and the characteristic polynomial of A is given by x square minus the trace, that is 1 plus 2 x plus the determinant, which is 2 minus 6, which comes as x square minus 3x minus 4. On factorization, we are going to get x minus 4 and x plus 1. Thus, it can be seen that the eigenvalues of A are lambda 1 is equal to 4 and lambda 2 is equal to -1. Since A is a 2 by 2 matrix and we have got two distinct eigenvalues, using the third result, we can clearly say that A is diagonalizable. So since A is diagonalizable by the earlier definition, we have that there exists a non-singular matrix C, that is determinant of C is non-zero, such that C inverse A times C is going to be some diagonal matrix D. Now we are left out to find out the matrix C. To find matrix C, we need to find the corresponding eigenvectors for the eigenvalues which we have got. Now let's start with lambda equal to 4. To consider A minus 4 times I times x is equal to 0, which gives us -3 2, 3, negative 2 times x, which is x1, x2 is equal to 0, 0. Performing row operation R2 changes to R2 plus R1, we get negative 3, 2, 0, 0. Here we have x1, x2, and here we have 0, 0. And this gives us negative 3x1 plus 2x2 is equal to 0. This gives us that x1 is equal to 2 over 3 x2. If I put x2 as 1, we get x1 as 2 over 3. Now just in case I want to avoid fraction, let me take x2 as 3. So in this case x1 will be 2, and therefore I will get 2 comma 3 is the eigenvector corresponding to lambda 1 equal to 4. Similar calculations for lambda 2 equal to negative 1 gives us that negative 1 comma 1 is the eigenvector corresponding to the second eigenvalue. Now we have got two eigenvectors, and this we are going to use to construct the non-singular matrix C. So C is given as the matrix 2, 3 column wise and negative 1, 1. As you can see that the first eigenvector 2, 3 represents the first column of C, while the second eigenvector negative 1, 1 represents the second column of the matrix C. And it is not difficult to see that the determinant of C is non-zero. Now for the last part, let us calculate the product C inverse A, C, and this should result in a diagonal matrix. C inverse is given by 1 over determinant of C, which is 1 over 5. We will be reversing the diagonal entries in C. So we have 1, 2 on the diagonal, and the non-diagonal entries need to be negative. So we'll have 1 and negative 3 here times A. A was the matrix 1, 2, 3, 2. And again we take the product with C. As earlier, let us first multiply these two matrices. And we get times 2, negative 1, 3, 1, which gives us 1 over 5. Again, multiplying these two matrices, we are going to get. And lastly, taking in the scalar 1 over 5, we get that this is equal to 4, 0, 0, negative 1, which is a diagonal matrix. And surprisingly, if you will see that the diagonal entries of this matrix are nothing but the eigenvalues of the corresponding matrix A. Now let us state our observation with respect to diagonalizability. So if A is diagonalizable, then the product C inverse A, C will be some diagonal matrix, where this diagonal matrix D will have the eigenvalues of A on its diagonal, and the non-singular matrix C will have columns as the eigenvectors which you are going to get for the matrix A. That's all for today. If you have understood the video, please like the video and also share it with your other friends who are interested in mathematics, and also subscribe to my channel for more videos. Thank you so much for watching and happy learning.